In this lesson, we'll be looking at rational functions. Basically, we're going to really focus on graphing here. Of course, a rational function is a quotient of two polynomials. These are functions that basically have fractions in them. And so we're going to graph f of x equals 1 over x by plotting points. Now, the first thing to notice here is x can't be 0. That's our restricted value. And so our domain would be everything except 0, negative infinity to 0, union 0 to infinity, where we have parentheses next to the 0 because we're not including 0. And let's go ahead and make a table. If I let x be 1, f of 1 would be 1 over 1, and we would get 1. If I plug in 2, f of 2 would be 1 over 2, and we'd get a half. And similarly, if we plug in 3, we'll get a third. Let me go ahead and plot these points. So you can see what's happening here. As x gets bigger, we're going to continue to get smaller. If you plug in 4, you'll get a fourth. If you plug in 5, you'll get a fifth. But notice we're never going to get to the x-axis. So let's see what's happening as we go to the left. What about if x were a half, for example? Well, let's go ahead and plug a half into the function. You get 1 over a half, or 1 divided by a half, and we'll multiply by the reciprocal, and we get 2. All right, and so what about if we plugged in a third? Well, similarly, we would get 3. And the same thing I could go to 1/4, 1/5, and so on. And what's happening is our points are going to get closer and closer to the y-axis, but they're never going to get there, similar to what was going on along the x-axis. And so notice what we have here. As we go to the right, we're approaching the x-axis, and going back to the left, this approaches the y-axis. In fact, we have what's called an asymptote at y equals 0. That would be the line y equals 0. Notice I'm making it dotted. And the reason why, it's really just a guide for the graph. It's not actually part of the graph when we draw the graph. It just is a guide. And then so that's our horizontal asymptote. And we also have one that's on the x-axis. That would be the line x equals 0, and that's our vertical asymptote. Now, what about on the other side of the vertical asymptote? On the left side, what if we have negative values of x? Let's go ahead and make a table. So if we plug in -1, f of -1 would be 1 over -1, which would give us -1. And if you plug in -2, you would get -1/2. So you can see what's happening here. The only difference with our outputs is they're going to have the opposite sign. So our input and our output both have opposite signs. And so we're going to get the same table just with all negatives. So if we plot those points, we are going to end up getting an arc on the other side that looks just like the one on the right side. In fact, you may have noticed we have symmetry here. This is what we call origin symmetry. This is an odd function. And by the way, when you're doing graphing, if you have a function that has some kind of symmetry, whether it's y-axis symmetry or origin symmetry, that can make things easier when you're plotting points, because if you get a point on one side, then you'll know a point on the opposite side using some symmetry. All right, let's move on, and now we're going to focus on asymptotes. Turns out they're a really important feature of rational functions when we're doing graphs. Okay, so it says, consider the following rational functions and their corresponding graphs. Determine the domain for each. So first of all, we're going to find the domain here. So our restricted value here is x, well, it can't be 1. And so our domain will be everything else except 1, negative infinity to 1, union 1 to infinity. Excuse me. Let's look at number 3. Now, first thing we'd want to do here is factor our denominator, and however you do that, you should be able to factor a trinomial. In this case, you get x plus 3 over x minus 2. And so we can see that our restricted values, let's see, if x is negative 3, we have a problem. Same thing with 2. And so those would make our denominator 0. So that means our domain is going to be everything except for negative 3 and 2. So let's see, we'll go from negative infinity to the smaller number, negative 3. Excuse me. And then we're omitting a negative 3, so we'll do a union negative 3 to the next number, which would be 2, and then we'll union that with 2 to infinity. So it looks kind of long or a little bit complicated, but all this really means is that our domain includes all real numbers except for negative 3 and 2. All right, if you look at number 4, you can see our restricted value is negative 2. And so our domain will be everything except for negative 2. All right, so now what I wanted to do here is let's look at the graphs and see if we can figure out something about vertical asymptotes. We'll also talk a little bit about the horizontal asymptotes. So if you look at this first graph at the bottom here, you can see that we have a vertical asymptote at x equals 1. Notice there's a horizontal asymptote at y equals 2. In the second graph, notice there's two vertical asymptotes, one at negative 3 and one at 2 at x equals 2. And then there's a horizontal asymptote as well right at y equals 0. Finally, on the last graph, it's a little bit harder to see, but there's a vertical asymptote at negative 2, and there is no horizontal asymptote, but notice we have this sideways asymptote, or what we actually call this an oblique asymptote. And so the most common ones that we'll work with are vertical and horizontal asymptotes, but on occasion we'll run into an oblique asymptote. Now, I'd like you to go ahead and look at what we did on 2, 3, and 4, and look at the relationship between our restricted values and our vertical asymptotes. In fact, you can see that wherever we have a restricted value, there is going to be a vertical asymptote. All right, so let's move on to the next slide. So for those values of x for which f of x is not defined, what do you notice about the graph? Actually, I didn't answer that question. Basically, we have a jump, or that's where we have those vertical asymptotes. Basically, the graph has a break or jump. So an asymptote is an invisible line that the graph of a function approaches. For a rational function that is simplified, if the function is undefined at x equals a, then x equals a is a vertical asymptote for f. So in other words, we have a restricted value at x equals a, and in fact that's where we're going to have a vertical asymptote on the graph. So the restricted values basically determine where our vertical asymptotes are going to be. So down here we're supposed to write the equation of any vertical asymptotes for each of the graphs of the following rational functions. So on number 5, you can see that x can't be 5. Now there's another way to find vertical asymptotes other than just looking at your denominator. Sometimes it won't be as obvious. What we really want to know is what value of x makes the denominator 0. So all you really need to do is set your denominator equal to 0, and when you solve for x, you'll find your restricted value, and of course that's where you're going to have your vertical asymptote. So on number 6, the way I would do this one is I would factor the denominator there. So you should be able to factor that. Actually, I'm sorry. I would normally factor it and I could get my restricted values from that. But what I wanted to show you here is all I need to do is set it equal to 0, my denominator, and we will factor that. And so you can see that our restricted values are going to be -4 and 2. And again, that's where our vertical asymptotes are going to be. On number 7, let's it's not it may or may not be obvious to you what your vertical asymptotes might be, but we can go ahead and set our denominator equal to 0. Now when we solve this equation, notice what happens here. We're going to take the square root of both sides. We get x is plus or minus 3i. So we have 3i and minus 3i. These are imaginary numbers. Now remember what I said, when it comes to graphing, I tell you to keep it real. We're just dealing with real numbers. We don't graph imaginary numbers when we're doing graphing. And so in this case, there are no real numbers that are a problem here. And so we're not going to have a vertical asymptote. All right, let's move on to the next slide. Let's talk about horizontal asymptotes. And you know, actually, I forgot to mention that on the last, let's go back to where we were here. The thing I want you to notice about horizontal asymptotes is they tell us what's going on the ends. You can see that in each of our graphs, the graphs are approaching the horizontal asymptotes on the end. And the same is true with oblique asymptotes. And so when you're dealing with horizontal or oblique asymptotes, they really indicate what's going on in terms of end behavior. Your graph eventually approaches a horizontal asymptote on the ends. Now it is possible that in the middle you could cross a horizontal asymptote. Again, horizontal asymptotes, the focus is on, or the main thing is, it indicates what our end behavior is going to be. With vertical asymptotes, you're never going to cross. So let me go back to where I was. Whoops, I went a little too far. Okay, so on horizontal asymptotes, let's see, it says, as x gets very large, both positively and negatively, the graph of a rational function usually approaches a horizontal asymptote on each end of its graph. That's what we were just talking about. Consider the following function in the corresponding table of values. So I've already plugged in these x values for you and solved for y. And you can see, let's look here first. As you know, we go from x is 10 to 100 to 1,000. Our outputs, or our y values, keep getting smaller, and they're approaching 0. The same thing's happening when you go in the other direction. So we go from -10 to -100 to -1,000, and you can see that the y values, or the output values, are getting super small, closer and closer to 0. And so again, the whole point of this is that as x gets really big, or really big negative, the value of the function is getting closer and closer to 0. All right, so here's our 3 cases. We're not going to prove these cases in this course. That's something you would do in pre-calculus or calculus. You would deal with a topic called limits. We're just going to go ahead and learn the 3 cases, and that's all we'll be using when we're finding horizontal asymptotes. So it says, first of all, in case 1, if the degree of the numerator is less than the degree of the denominator, then f has a horizontal asymptote at y equals 0. So notice in my example here, f of x equals x plus 1 over x squared plus x minus 6. The degree of the numerator is 1, the degree of the denominator is 2, and so this would be the first case where the numerator has a degree that's smaller than the degree of the denominator. And this is the one that I will call bottom heavy, because the degree is bigger in the bottom. So in this case, the horizontal asymptote will be at y equals 0. So I've got these little phrases that will hopefully help you remember the three cases. In case 2, if the degree of the numerator is equal to the degree of the denominator, then f has a horizontal asymptote at y equals the coefficient of the leading term in the numerator divided by the coefficient of the leading term in the denominator. Well, it sounds kind of complicated, but you can see that our degrees are 1 for the numerator and denominator. So this is what I call the balanced case. And in this case, the way that what this is saying is, if you look at the coefficients, I missed that. If you look at the coefficients here, we have 2 over 1, the coefficients of our leading terms. Y is going to equal 2 over 1, which is 2. And so that's the balanced case. Now in case 3, it says if the degree of the numerator is greater than the degree of the denominator, then f has no horizontal asymptotes. So this is like the opposite of case 1. The numerator has the bigger degree. So notice in my example here, f of x equals x squared minus 2x minus 3 over x plus 2. The degree in the numerator is 2. The degree in the denominator is 1. And so this one is what I call top-heavy, and this is the case where we have no horizontal asymptote. All right, so let's go ahead and practice on numbers 8 through 11, where we're going to be finding vertical and horizontal asymptotes. So on number 8, so first of all, you can see that x can't be 4, so that's our restricted value, so we know that's where we're going to have a vertical asymptote at x equals 4. For the horizontal asymptote, notice this would be case 1, because the degree of the numerator is 0, the degree of the denominator is 1, and so this one is what I call bottom heavy, and so the asymptote, that's case 1, where we get a horizontal asymptote of y equals 0. All right, you may want to try the other three, or at some point you might try them and then watch my video solution. Let's go ahead and look at number 9. So to find the vertical asymptotes, let's go ahead and set our denominator equal to 0. This is similar to one that we did previously, where you get imaginary answers here, which indicates that there are no real number restrictions on your denominator for x, and so we don't have a vertical asymptote. And as far as the three cases for horizontal asymptotes, this is the second case where we're balanced. So we'll look at the coefficients, 5 over 1, so y equals 5. So on number 10, this is also the balanced case. Actually, before I do that, let me do the vertical asymptotes. So I'm just going to go ahead and factor the denominator here. So you can see that our restricted values are 7 and negative 5, and that's where we're going to have our vertical asymptotes. Again, I said this was the balanced case, so if you look at the coefficients, now be careful in the numerator, the leading term is negative 3x squared, and so you're going to use negative 3 over 1, so y equals negative 3. All right, last problem here. If we set the denominator equal to 0 and solve for x, let's see, I subtracted 3 on both sides. Let me divide by 2. We get negative 3 halves, and so that's our restricted value, and that's where we'll have our vertical asymptote. As far as horizontal asymptotes are concerned, this is case 3, where we're top heavy, and so there is no horizontal asymptote. In fact, it turns out this is the case where we have an oblique asymptote. So case 3, we don't have a horizontal asymptote, we're going to have an oblique asymptote. All right, let's move on. On number 12 here, it says find any oblique asymptotes for each of the following rational functions. So these are both of these problems, you'll notice the degree of the numerator is greater. They're both top heavy. And so this is the case where we do have oblique asymptotes. So basically what we're going to end up doing is just doing division here, and that's going to help us to find the oblique asymptotes. So I'm going to use synthetic division on the first one here. So let's go ahead and drop our 1. We'll multiply -1 times 1, we get -1. When we add, we get -5. Multiply, we get 5. When we add, we get 8. And so the answer here is x minus 5 plus 8 over x plus 1. Now it turns out that this x minus 5 is going to be our oblique asymptote. It's going to be y equals x minus 5. Let me see if I can explain this in a way that makes sense. Basically what's going on here is we found another way to write f of x. It's basically the answer when we do the division. And here's the thing. As x approaches infinity, or as x gets bigger and bigger, notice what happens to 8 over x plus 1. You're going to have 8 over a bigger and bigger number. Like if x is 1,000, 8 over 1,000 plus 1, you're getting small. And as x gets even bigger, you're going to get closer and closer to 0. Well, if this is getting closer to 0, that means the value of the function, or f of x or y, is going to be x minus 5. So what we're saying here is as x approaches infinity, the graph of f approaches y equals x minus 5. This part here is just going to go to 0 as x gets really big. All right, let's move on to number 13. So notice here we're doing division, and we're not going to be able to use synthetic division because this is not a quadratic expression that we're dividing by here. I'm going to go ahead and make that note off to the right here. So our divisor is quadratic. We can't even use synthetic division. So we're going to use long division on this one. So I've set it up. So remember, we want to look at our leading terms. And we're going to ask ourselves, what times x squared will give us x cubed? And that would just be x. Now the other way to do that is just take x cubed over x squared. And of course, if you divide that, you do get x. So now that we've got the x there, we're going to multiply x times our divisor, which means we got to distribute here. We're going to get x times x squared, which is x cubed. X times a plus 2x is a plus 2x squared. And x times a minus 1 is going to be minus x. And so let's go ahead and subtract. X cubed minus x cubed is 0. We should always get 0 for that first term. And then a minus x squared minus 2x squared. That would be a -1 and -2. That's negative 3x squared. Then you have x minus a minus x. That becomes a plus x. X plus x is 2x. And then let's bring down the 4. And so now we're working with a leading term here of negative 3x squared. I need to know what times x squared gives me negative 3x squared. And that's going to be a minus 3. Again, you could just write negative 3x squared over x squared, and you notice you do get negative 3 when you simplify that. So now let's multiply our divisor by negative 3. Negative 3 times x squared is negative 3x squared. Negative 3 times 2x is negative 6x. And negative 3 times a negative 1 is a positive 3. And let's go ahead and subtract from what's above. Negative 3x squared minus a negative 3x squared. We're going to add there. And we do get 0. 2x minus negative 6x. That becomes plus 6x, so we'll get 8x. And negative 4 minus 3 is negative 7. Now before I put in my answer here, I need to erase this area here. Let me take care of that. Oops, hold on just a second. I got to make that a little bigger. Okay, so we're going to get x minus 3, our quotient, plus the remainder over our divisor. And so again, it's this part here. Whoops, wrong tool. That's the part that's going to tell me what my oblique asymptote is. So I'll use OA for oblique asymptote. So y equals x minus 3. All right. I'm going to go ahead and stop the video here, and I'll do a second video for the rest of the lesson.